So a week before my Memorial Day weekend, I was hyped. The weather was looking beautiful. I was excited to play outside and of course work on my Breakthrough Junior Challenge. Fast forward a week and hey Siri, how's the weather?
Look around you, smart one. It's obviously raining. You think we're smart? Shut up.
Are meteorologists doing their jobs? Well, it turns out that weather is a lot harder to predict than what you'd expect. And this is because weather is a chaotic system. A chaotic system is one that's sensitive to initial conditions. Slight changes in factors such as temperature, pressure, and wind speed can all change future weather drastically. In fact, chaos was first discovered when Edward Lorenz was trying to predict the weather at MIT. He used this set of differential equations to model the weather and accidentally discovered chaos when he found that a rounded set of initial conditions completely changed the outcome values. What is that? Oh my god! Oh shit! Lorenz's set of equations, which are sensitive to initial conditions, can be described through the Lorenz attractor. As you can see, this path never follows itself. If it did, the conditions would be exactly the same, and the line would continuously loop and be predictable. One slight change in initial conditions can alter the outcome of the system completely. Here, I have two attractors with slightly different initial conditions. Notice how the paths have already diverged. Keep in mind that the Lorenz equations are not random. If you use the exact same initial conditions, you'll get the exact same results, and the lines wouldn't diverge. It may be easy in the theoretical, but setting exact initial conditions is pretty much impossible in real life. We can demonstrate this by using the double pendulum, which exhibits chaotic motion. I'll start two at a similar position. You can see that they start off with similar paths, but soon the paths become completely different. This is because although the pendulum is deterministic, meaning that one specific initial input will lead to one specific output every time, it's physically impossible for us to replicate initial conditions on this double pendulum, because you would need to be infinitely exact. Although chaos can seem impossible to represent, because chaotic systems are so hard to predict, there are still rules that describe chaos, and any set of rules has structure. If we observe the limits of chaos, we can dive into the world of fractals. A fractal is a geometric pattern that has self-similarity. No matter how far you zoom into a fractal, you'll see repeating patterns. Let's see if we can make a fractal using our double pendulum. We'll make a fractal by using a grid with two axes, theta 1 and theta 2. We'll record the amount of time it takes for the pendulum to flip for every combination of theta 1 and 2 as initial conditions. Each time will correspond to a color on the grid, and the color black will correspond to no flip at all. Of course, there are infinite combinations for theta 1 and 2, so we'll start off by using increments of 30 degrees. It definitely looks interesting. Let's try it with increments of 20. Pretty cool. Now let's try increments of 10 degrees. We can see that a detailed image is starting to form. In a perfect world where we could exactly replicate initial conditions and use an infinitely fine grid, fractals would form at the boundaries between the colored and black area where the pendulum flips and doesn't. I think our approximation is pretty cool though, don't you? Oh my god! Oh shit!